Hello everyone, this is an audio recording for visually impaired student. Today I am going to read a chapter from Pradeep in Organic Chemistry written by Dr. K. Bassi, named Chemistry of Actinides. Actinides consist a series of elements following actinum Z is equal to 89 in the seventh period of the periodic table. Actinide belong to 5F block as they are named by the gradual filling of 5F subshell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides, which follow lanthanum Z is equal to 57, involve the gradual filling of 4F subshell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinum Z is equal to 89. This series of 14 elements is called actinides. Actinides, along with lanthanides, constitute complete F block element. The ending id in actinides is not appropriate because it's more correctly named negative ions such as oxide or chloride. Actinides were also named as actinones by a group of scientists. However, the ending on is used preferably for non-metals such as boron, silicon, whereas all the actinides are distinct metallic. IUPAC has now recommended this element to be called actinoids with the ending oid rather than being actinide or actinone. However, it is unfortunate that people still call these elements by their earlier name as actinides. Before World War II, the only natural occurring actinides, namely thorium, protactinium, and uranium, were known. Uranium is the heaviest natural occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reactions. These elements are named man made or synthetic elements. Another name coined for this element is a transference element. Transference elements are elements that have atomic number greater than 92. Let us now discuss the interesting aspect of the chemistry of actinides. Position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of noble gas written as xenon 54, 6s2, 4f14, 5d10, 6p6. After radon, the 7s and 7p orbital gain stability relative to 5f orbital because s and p are more penetrating than the d and f orbital. As a result, the next two electrons are being filled in a 7s orbital, which mark the appearance of new element francium Z is equal to 87 and radium Z is equal to 88 belong to S block of element. After the addition of two electrons in the radon core, the 5f and 60 electron penetrate the 7s orbital. The least penetrating f orbital are stabilized on account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 electrons from thorium Z is equal to 19 to Z is equal to 103 enter the 5f shell. It is important to note that around actinum, both the 5f and 60 subshell possesses almost similar energy. Because of similar energy of 5f and 60 subshell, the incoming electron may enter either of the two subshell, which result in the uncertainty of the electronic configuration. As a result, it is doubtful whether the electron enter the 5 orbital or not. For example, the electronic configuration of thorium Z is equal to 90 may be written as either 5f0 6d2 7s2 or 5f1 6d1 7s2. However, once filling start in 5f5 orbital, the 5f subshell become more and more stable. As a result, from uranium onward, the 5f subshell become more stable, shown in figure 5.1. Thus, all the incoming electrons start filling progressively in f orbital. The general electronic configuration of actinides can be assigned Rn 5f0 to 14, 6d0 to 1, 7s2. General characteristics of actinides. Some of the general characteristics of actinides are detailed below. Electronic configuration. As already discussed in section 5.1, The actinides involve the gradual filling of 5F subshell. The electronic configuration of the tilted actinium Z is equal to 89 is red and 6D1 7s2. Thus, from thorium onward, the 5F subshells start progressively filled. The general electronic configuration of the atom of actinides in the ground state may be written as Rn 5F1 to 14 6D 0 to 1 7s2. The detailed electronic configuration of element are represented in table 5.1. Second, physical property. Some of the physical property of the actinides are present in figure 5.2, which are described below. Melting and boiling point. The melting and boiling point of the actinides are moderately high but are lower than those of the transition element. An inspection of the table 5.2 reveals that there is no regular trend in the melting and boiling point of the non-actinides. Density. An inspection of the table 5.2 reveals that the element near uranium have very high density. Americum resemble the corresponding lanthanide. Europium is being less dense than its neighbor. Fourth, ionic radii and the actinide contraction. The size of the actinide ion decreases regularly along the actinide series. This is because with increasing atomic number, the extra charge on the nucleus is poorly screened by the F electron. This steady decrease in ionic radii with increase in atomic number is called actinide contraction. A comparison of M3 positive ionic radii of actinide with those of the lanthanide reveal that the actinide and lanthanide ion are very similar in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of M3 positive and M4 positive ion in case of actinide shown in figure 5.2. It is interesting to note that there is a decrease in atomic radii from thorium to uranium, which may be due to decrease in the most stable oxidation state from plus 4 to plus 6. In the other word, the metallic bonding from thorium to uranium may be considered to consist of M and positive ion with a total of any electron for atom. After plutonium, the metallic radius increased significantly again, which may reflect the increasing lanthanide like behavior of the later actinide, in which the preferred oxidation state is plus 3 with only 3 electron per atom available for metallic bonding. Fifth is oxidation state. The actinide elements show a great range of oxidation state than the lanthanide, particularly in the earlier part of the series. The different oxidation of the actinide element are shown in table 5.3. The plus 2 oxidation state in case of actinide is very rare. Am2 positive has an electronic configuration 5F sun. It is analog to europium 2 positive in the lanthanide but exists only in the solid state as the fluoride AmF2. On the other hand, Cl2 negative, Es2 negative, Fm2 positive, Md2 positive, and NO2 positive exist as ion in solution. The property of divalent actine resemble more closely to Ba2 positive in group 2. The most stable plus 2 oxidation state is exhibited by nobelium as NO2 positive and corresponding to stable 5F14 arrangement. The plus 3 oxidation state is the most common oxidation state among all the actinides. However, this is not always the most stable oxidation state in the actinides. The first four elements TH, Pa, U, and P do not show plus 3 oxidation state as the most stable oxidation state. For example, U3 positive is readily oxidized in air as well as in solution. Interestingly, the most stable oxidation state of element up to uranium is the one involving all the valence electron. Thus, the most stable oxidation state of TH, Pa, and U are plus 4, plus 5, plus 6 respectively. Although Neptunium show the oxidation state is plus 7 by involving all its valence electron. It is not the most stable state. This is because Np in plus 7 oxidation state is highly oxidizing and the most stable state is plus 5. The plus 4 oxidation state is exhibited by all the elements from TH atomic number 92, CF atomic number 96. However, Pa and Np display the most important plus for oxidation state. The M4 positive ion are known in the acid solution and are precipitated by FPO43 negative and IO3 negative. The element all form dioxide MO2 and fluoride MF4. The plus 5 oxidation state is exhibited by all the element from Pa Z is equal to 91 to Am Z is equal to 95. However, plus 5 oxidation state is more stable for Pa and Np. It is important to note that M5 positive ion do not occur in solution as such. In fact, these states occur as their oxocation, such as MO2 positive ion. A few solid compounds are known, whereas in solution these ions dispropagated rapidly. UO2 positive plus 4H positive give U4 positive plus UO2 2 positive plus 2 of H2O. The plus 4 oxidation state is exhibited by lower actinide in the form of their fluoride. The plus 6 oxidation state is more commonly as the dioxo ion MO22 positive. The ion MO22 positive is linear and exists both in solid as well as in solution. One of the most commonly encountered compound of uranium is plus 4 oxidation state is uralide nitrate dihydrate UO2 NO3 twice 2H2O. It consists of linear UO2 positive ions surrounded by two NO3 negative ions and water molecule as shown in figure 5.3. The NO3 negative group is bidentate and therefore two oxygen from each NO3 negative are bounded to. Uranium. Oxygen atom from the two water molecule also bond to uranium. Thus, the coordination number around uranium is 8. The UO2 positive unit in the compound UO2 NO3 twice H2O2 is perpendicular to a hexagon of 6 oxygen atom form 4 from bidentate NO3 group and 2 from the water molecule. The lower oxidation state are ionic while the higher oxidation state are increasingly covalent. The plus 7 oxidation state is known only in the oxocation of Np and Pu when alkaline solutions are oxidized by O3. The important oxoanion known in case of Np and Pu are NpO4 OH twice 3 negative and PuO6 3 negative. 6. Color of the ions. Actinides ions are mostly colored. The color of a particular actinide ion depends upon the number of electrons present in 5f orbital. The color of the actinide ion arises mainly due to FF transition. The color of the characteristic cation formed by the actinide ion in aqueous solution are given in table 5.4. In addition to FF transition in actinide, the color can also rises due to FD transition as well as charge transfer transition. The color of the actinide ion solution because of FF transition occur in a visible and UV reasons. We have already encountered this FF type of transition in case of lanthanide as well as since the 5f electron in case of actinides are projected out more in space than the 4f electron in lanthanides. These 5f electrons are strongly influenced by the ligand field of ligands. These make the absorption spectra of the actinides more complex compared to the straightforward spectra of lanthanide. A complex spectra is always different two characteristics easily. It has been experimentally found that the absorption due to FF transition in case of actinide are nearly 10 times stronger and 2 times broader than FF transition of lanthanide ions. The energy difference between 5f and 6d orbital in case of actinides being smaller than 4f and 5d orbital in case of the lanthanides. The actinide ion invariously absorb light of lower frequency. As a result, the allowed and very strong FD transition lie in the UV region and therefore do not influence the color of the actinide ion. It has been observed that the actinide ion in higher oxidation state display predominantly charged transfer spectra. This spectra is exhibited only by the higher oxidation state ion, which can easily oxidize the ligand. It is important to note that the lanthanide do not exhibit charged transfer spectra because lanthanide do not display oxidation state higher than 4. Magnetic property. The actinide shows similar magnetic property to lanthanide in terms of magnetic moment with the number of unpaired electron. This is shown clearly in figure 5.4 where the magnetic moment in Bm are plotted against the number of unpaired electron. It is important to note that the high valence state have been chosen for 5f1, 5f2, 5f3 and 5f4 ion which show the close similarity. Magnetic moment value for the isoelectronic actinide ions are lower than the lanthanide ion. Example Np plus 6, Ce plus 3, Np5, Npr plus 3. Np plus 4 and D plus 3. It is due to fact that the 5f electron in actinides are projected more in space to the crystal field. As a result, the partial quenching of orbital occur by the crystal field effect. Eighth is reactivity. Actinides are highly reactive metal. These these react with dinitrogen and form non-stoichiometric hydride with the formula MH2 or MH3. They react with hot water and furnishing in air, forming an oxide coating. The actinides react readily with HCl, but reaction with other acid is lower than expected. These metals are basic and do not react with sodium hydroxide. The actinides react directly with the halogen to form a variety of halides. The redox potential for the M3 positive slash M couple are about minus 1.9 volt. Thorium and uranium chemistry has been explored in detail. Some of the journal method for preparing compound of actinide are given below in figure 5.5. Occurrence and isolation of actinides. All the elements beyond actinium in the periodic table are radioactive. As a result, the nuclei of all the actinide are unstable and undergo radioactive decay. Among the actinide, uranium is the heaviest natural occurring element with the abundance of 2.4 ppm in the earth crust. Among the actinide, Th and U occur on the earth because the isotope of U92 235, U92 238, Th90 232, and Pu 244 have half-life sufficiently long in view of the fact that the earth was formed several million years ago. Uranium. Since uranium is the most important of all the actinide, its chemistry will be discussed in more detail. The primary natural source of the uranium is pitchblende or uranide, which have the empirical formula U3O8. It is mixed oxide contain uranium both in 4 and 6 oxidation state as UO2 dot 2 UO3. The important ore are caronite, K2O.2UO3, V2O5.3H2O, or K2UO2 twice VO4 twice dot 3H2O. Utenite, CaUO2 twice PO4 twice dot 8H2O. Calcium caronite, CaO dot 2 UO3 dot V2O5 dot NH2O. Extraction of uranium. As already mentioned, the main source of uranium is pitchblende. The detail of extraction of uranium involve the following step. Concentration. The ore is cast into the fine powder and subjected to conventional gravity separation to remove the lighter impurity. Second, roasting. The concentrated ore is roasted on the hearth of the battery furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic, and antimony. S plus O2 give SO2. As plus 3 molecule of O2 give 2 molecule of As2O3. 4 molecule of Sb plus 3 molecule of O2, it will give 2 molecule of Sb2O3. Third, acid treatment. The roasted ore is treated with dilute H2SO4 in the presence of an oxidized agent such as MnO2 or NaClO3. These treatments convert uranium to a soluble uranyl sulfide UO2SO4. The roasted ore can be converted to a solution of UO2 and O3 twice by dissolving the ore in the nitric acid. U3O8 plus 3H2SO4 plus O2 give 3 UO2SO4 plus 3H2O. Fourth, treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution of uryl sulfide precipitate it as ammonium uranyl carbonate NH4 tetra UO2CO3 thrice. UO2SO4 plus 3 NH4 twice CO3 give NH4 tetra UO2CO3 thrice plus NH4 twice SO4, which upon ignition give U3O8 as NH4 tetra UO2CO3 thrice give U3O8 plus 9 CO2 plus 12 NH3 plus 6 H2O plus O2. Alternatively, ammonia is added to the solution of uranium sulfate obtained in step 3. Acid treatment. These give rise to the bright yellow precipitate of ammonium diuranate. 2 UO2SO4 plus 6 ammonia plus 3 water molecule give NH4 twice U2O7 solid plus 2 NH4 twice SO4. This precipitate is often called the yellow cake. This cake on heating give rise to mix oxide uranium plus 4 and uranium plus 6 oxide U3O8 equivalent to UO2.2UO3. 9 molecule of NH4 twice U2O7 solid, it will give 6 molecule of U3O8 plus 14 molecule of ammonia plus 15 molecule of H2O plus N2. Fifth, conversion into uranium dioxide. The mixed uranium oxide U3O8 is reduced to UO2 by heating either with charcoal or with hydrogen. U3O8 plus 2H2O give 3 molecule of UO2 plus 2 molecule of H2O. 6. Production of uranium. Elemental uranium can be produced from uranium dioxide by using either of two methods. First, UO2 is heated with the vapor of HF to form uranium fluoride, which in turn react with magnesium to yield uranium metal. UO2 plus 4HF give UF4 plus 2H2O. UF4 plus 2 magnesium, it will give U plus 2 MgF2. Or by converting UO2 to a volatile uranium tetrachloride by heating it with the elemental chlorine in the presence of charcoal. This is followed by reduction with elemental sodium. UO2 plus chlorine give UO2Cl2. UO2Cl2 plus chlorine give UCl4 plus O2. UCl4 plus ammonia sodium give U plus 4 NaCl. All the steps detailed above can be summarized in the flow sheet diagram for the extraction of uranium. Chemistry of separation of neptunium, plutonium and americium from uranium. The three elements Np, Pu and Am that follow U in the actinide series are produced mainly from uranium in the nuclear reactor. If you recall, uranium is the oldest known element among the actinide. Natural occurring uranium contains two main isotopes U92-238 and U92-235, which occur in the ratio 99.3% and zero point 0.7 respectively. This is another isotope of U92-233, which occur in traces only. Neptunium and plutonium, named after the planet Neptune and Pluto, were prepared for the first time in 1940 by a team of calibrated scientists by bombarding uranium with neutrons in the cyclotron in Berkeley, USA. Both the elements are now obtained from spent uranium fuel element of nuclear reactor, where they are formed by the capturing of neutron produces in the fission of U92-235 fuel as isotope of plutonium, Pu, can also be prepared by N2N reaction in which a first neutron is added with the subsequent loss of two neutrons without allowing time for the intermediate product to decay. U92-238 N, 2N give U92-237 minus beta. It will give NP93-237. Americium can be obtained from the isotopes of plutonium by the success N and gamma reaction in the nuclear reactor. Pu94-239 N gamma give Pu94-240, give Pu94-241, give in the presence of beta it will give AM95-241. The yield of the heavier element is controlled by two factors: the half-life of the various isotopes by their ability to absorb neutron. It is important to note that the stepwise addition of slow neutron is very difficult. A quick method is to bombarding the nucleus with a large number of fast electrons without leaving time for the intermediate product to decay. For example, uranium 92 238 add as fast neutron and then loses two neutron to form an isotope of neptunium according to the reaction. U92-238 N2N give uranium 92-237, beta give Pu 93-237. The separation of these elements from uranium is extremely difficult and hazardous. It is because this element, including the starting material, are not only highly radioactive but also give the highly radioactive fission product. Plutonium especially is extremely toxic. A dose as small as 10 ki power minus 6 gram may be fatal, while smaller doses are acrygenic. The separation of NP, Pu, and Am from uranium are based on the following chemistry. First, stability of oxidation state. A steady decrease in the stability of high oxidation state with increase in atomic number have been observed with increase in atomic number. The order of stability of major ion involved are Am3 positive greater than Pu3 positive greater than Np3 positive and uranium 4 positive. Whereas the order in case of the oxo ions are UO2 2 positive, NPO2 2 positive, PuO2 2 positive, AMO2 2 positive. Separation of these elements from uranium from which they are obtained in a nuclear reactor from fission product and from one another can thus be achieved by adjusting the solution containing them to a suitable redox potential and then using solvent extraction or precipitation. For example, Pu can be oxidized to PuO2 positive while Am remain as Am3 positive. Thus, plutonium Pu can be removed by solvent extraction whereas americium can be precipitated as AmF3. Second, extraction into organic solvent. The MnO2 positive ion from solution can be extracted into organic solvent. The M4 positive ions are extracted into tributyl phosphide in kerosene from 6M HNO3 solution, whereas M3 positive ion are extracted from 10 to 16 M HNO3. Third, precipitation reaction. Actinide in the plus 3 and plus 4 oxidation state can be precipitated as their fluoride or phosphate from acid solution. The higher oxidation state give either no precipitate or can be prevented from precipitation by complex formation with sulfate ion. Fourth, ion exchange method. Ion exchange method are commonly used in separation for small amount of material as in the separation of americium. AM. Spent uranium fuel rod removal from the nuclear reactor can be used to extract NP and PU in kilogram quantity, whereas AM in 100 gram quantity. This reprocessing of nuclear fuel rods is an important technology as this help to extract new element that may be used as nuclear fuel. Spent fuel rods are dipped in the bond of the water for several days to allow them to cool. During this dipping period, the intense radioactive isotope with short half-life such as I-53 155 half is 8.04 days lose most of their reactivity. The fuel rods are dissolved in 7-MHNO3 and extracted with 30% tributyl phosphate in kerosene. The extraction coefficient of the actinide in 7-NHNO3 solution containing 30% of tributyl phosphate in kerosene are Pu4 positive greater than PuO2 2 positive. NP4 positive nearly equal to NPO2 positive greater than PU3 positive and UO2 2 positive greater than NPO2 positive greater than PuO2 2 positive. M3 ion have low extraction coefficient in 7 and HNO3. As a result, nitrate of UO2 positive and PU4 positive are preferably extracted in tributyl phosphate, leaving the other actinide, namely NP and AM, along with the other fusing product in aqueous solvent. It is also important to note that 7 and HNO3 cannot oxidize PU4 positive to higher oxidation state. Pu5 and Pu6 reduction of UO2 positive, Pu4 positive, nitrate solution with SO2, NH2OH or FeNH2SO3 twice give aqueous solution of Pu plus 3 without affecting the reduction of UO2 to positive. Thus, Pu4 positive is reduced to Pu3 positive which enter the aqueous phase while UO2 2 positive remain unchanged in the organic layer. UO2 positive species present in kerosene oil on treatment with 0.2 normal HNO3 gives UO2 NO3 twice in aqueous solution which on evaporating leave a solid mass of composition UO2 H NO3 twice 6H2O. On heating this hydrated solid compound to 400 degrees Celsius give UO3 which upon further reduction yield UO2. On the other hand, aqueous solution of reduced Pu plus 3 oxidation solution on treatment with nitrous acid get oxidized to Pu4. This solution react with oxalic acid to give crystalline precipitate of the composition Pu C2O4 twice dot 6H2O. Heating the hydrated compound to 300 degrees Celsius give PuO2. The whole sequence of step outlined in the process. The separation of other actinide, namely NP and AM, can be achieved by the use of appropriate oxidation reduction cycle coupled with solvent extraction. For example, Pu3 positive in aqueous nitric acid can be oxidized to PuO2 positive by an oxidation coupled with E naught greater than 1.02 followed by extraction into hexane, whereas AM3 positive is unchanged and remaining in aqueous solution. Transuranic element with an atomic number greater than 92 are called transuranic element. Before the Second World War, the element thorium Z is equal to 90, protonium Z is equal to 91 and uranium Z is equal to 92 were located below hafnium, tantalum and tungsten in the periodic table. The synthesis of neptunium, a new element with atomic number 93 by M.C. Millen and Abelson in 1914, was demonstrated bombarding uranium with neutron U and 92 to 38 plus N01, it will give U92 to 39 minus beta, it will give NP 93 to 39. This newly discovered element should be positioned immediately to the right of tungsten below rhenium. However, the property of neptunium resembles more with uranium further than rhenium. It was the discovery of neptunium followed by the sequence synthesis of the new element that were responsible for the new series of elements called the actinide series. All the transition elements are radioactive in nature and have short life period. Neptunium Z is equal to 933, plutonium Z is equal to 94, and americium 95 were unknown period to their synthetic preparation while nuclear reaction. However, these elements were later found to be present in trace quantity in uranium ore. Synthetic routes to transference element. There are two synthetic routes which are commonly used for the synthesis of transferic element. A neutron may be captured by the nucleus with the emission of gamma ray reaction. The neutron increases with mass number of nucleus by 1 unity and some energy is released as gamma radiation. Further neutrons may be added in similar way. Addition of neutron increase the neutron to proton N by P ratio. This makes nucleus unstable because it contains too many neutrons. As a result, the nuclei decay by converting a neutron into a proton or a beta particle. This reduces the N by P ratio and also increases the atomic number by 1. Thus, a new element is formed. The other method involving the capture of small ion by the heavy nucleus. This is possible only if the bombarding particle have sufficient energy to overcome the Coulombic repulsion between the ion and heavy nucleus. The smaller ion are accelerated in a linear accelerator or cyclotron to possess sufficient kinetic energy. The simplest ion used in the alpha particle, for example, a helium nucleus. This increases the atomic mass unit by several units and the atomic number by 2 units. For example, Pu 94 to 44 plus helium 24, it will give Cm 96 to 48, or Am 95 to 41 plus helium 24, it will give Bk 97 to 43 plus 2 and 01. Synthesis of transference element. All the transferinic elements have been prepared by nuclear reaction which involve bombarding with the either the neutron, alpha particle or other small nuclei. Preparation of neptunium. It was prepared by M.C. Millen and Absalon in 1914 at USA by bombarding uranium with slow neutron when U92-239 is obtained. U92-238 plus N01 is give U92-239 plus gamma ray. U92-239 being unstable emitted beta particle and result in the formation of NP after the name of the planet Neptune. U92-239 it will give NP93-239 plus electron minus 1 2.31 Ds. Preparation of plutonium Z is equal to 94. It was discovered by Cabork and his co-worker during the beta decay of neptunium 239. And P93 239 it will give Pu94 239 plus electron minus 1. 2.42 multiplied 10 to the power 4 years. Plutonium was named after the name of the planet Pluto. Preparation of americium Z is equal to 95. Americium was synthesized by bombarding U92-238 with alpha particle as U92-238 plus helium, it will give Pu94-241 plus N01. Pu94-241, it will give americium 95-241 plus electron minus 1 470 years. Preparation of Uranium. Yttrium was synthesized by bombarding Pu-94-239 with alpha particle as Pu-94-239 plus He24. It will give Cm96-242 plus N01, 162.5 days. Preparation of berkelium. Berkelium was synthesized by Seaborg and his co-worker by bombarding americium with high-speed alpha particle. AM 95 to 41 plus helium, it will give BK plus 2 and 01. Preparation of californium. Californium was synthesized by bombarding curium 242 with alpha particle. Preparation of einsteinium. Einsteinium was synthesized by bombarding U-238 nucleus with accelerated nitrogen nuclei. Two isotopes of californium have been identified. U92-238 plus N714, it will give ES99-47 plus 5 and 01. It can also be prepared by bombarding isotope of californium 250 with the neutron californium 253 obtaining during bombarding process result in beta decay during einsteinium. Preparation of franium. Franium was synthesized by bombarding einsteinium with neutron as ES99253 plus N01. It will give ES99254 plus gamma ray. ES99254, it will give FM100 254 plus E minus 10. Preparation of mendelevium. Mendelevium was synthesized by bombarding einsteinium 253 with neutron as alpha particle ES99 253 plus He24. It will give MD101 256 plus N01. Preparation of nibolium. Nibolium was synthesized by bombarding curium 246 with accelerated striped carbon. Cm96 246 plus C612. It will give NO102 254 plus 4 N01. Preparation of Lutetium. Lutetium was synthesized by bombarding californium 250 with accelerated boron nuclei. CF98 290 plus B511. It will give LW 103 257 plus 4N01. A summary of the synthetic of trans element along the half-life of the element given in table 5.5. Later or heavier actinide element. The element from uranium onward, namely uranium, Bk, Cf, Es, Fm, Md, No, and Lw are named as later actinides. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. The availability of some of the accessible isotopes are given in table 5.6. It is clear from the table that uranium is available only in the microscopic quantities, whereas the later actinides above atomic number 100 have been prepared only in minute quantities. In other words, the later actinides are available in tracer amounts. It is interesting to note that the later actinides show close resemblance to the lanthanides. However, the actinides can be easily separated from the lanthanide because the actinides readily form complexes. For example, the actinides react with the concentrated HCl to form the corresponding chlorocomplex. If both group of ions are absorbed on the cation exchange column, the actinides can be eluted more conventionally with concentrated HCl. After eluting the actinides can be separated from each other by ion exchange using citrate solution to elate them. It is interesting to note that the order in which the tripositive actinide ion are elated show a close similarity to the order in which the tripositive lanthanide ions are elated. Figure 5.7 display the elution diagram for the actinides and the lanthanides element. The first identification of the element from americium to mendelevium on the weightable scale was made through illusion. All the actinide with atomic number 96 to 103 CM, BK, CF, ES, FM, MD, NO, and LW with the exception of NO have plus 3 as the most stable oxidation state. The most stable oxidation state of Nebolium is plus 2. This is because it was the most favorable F14 electronic configuration. Actinides with atomic number 98 to 102. Californium 98 to Nebolium Z is equal to 102. Also display plus 2 oxidation state. Except for Nebolium plus 2 oxidation state is strongly reducing in nature. Higher oxidation state of uranium Cm plus 4 are found in a solid state in compounds such as CmF4 or RbCmF5. CmF4 plus RbF5 give RbCmF5. Similarly, Bk compounds are stable in the plus 4 oxidation states such as BkO2 and CS2 BkCl6. Z is equal to 104 exists only in the plus 3 oxidation state and resist oxidation and reduction. This resistance to oxidation and reduction illustrated the stability of an F14 electronic configuration. The element up to atomic number 100 undergo radioactive decay mainly by emitting alpha particle or beta particle. The later element become increasingly unstable as the atomic number increase. Nibolium is extremely unstable and has a half-life of only 3 seconds. Element beyond Z is equal to 103. The actinide series is complete at Z is equal to 103. We have already learned the half-life of the later actinide beyond atomic number 100 decreases considerably. For example, the half-life of nibolium is only 3 seconds. It has been calculated that the half-life of the element will decreases further as new element are discovered. The half-life of an element with an atomic number 108 is expected to be very short, about 10 to the power minus 4 to 10 to the power minus 6 second due to spontaneous decay. As a result, it is extremely difficult to synthesize and study the chemistry of element beyond 108. However, this difficult have not dampened the spirit of the scientists and they have been successful in discovering element up to atomic number 10112. Out of 112 non-element, element up to atomic number 109 have so far been named. A major controversy came to light over naming this element. The choice of the name of the element belonged to the discoverer. In case of prostoactinoid, 3 nuclear facility are in competition for the synthesis of each of the now newly discovered element. The facilities are at Berkeley, California, USA, Duban, USA, and Germany. It is extremely difficult to identify which nuclear facility had the true calm. For example, the discovery of element 104 was claimed by both Berkeley and Russia group. The American named the element Rutherfordium after Ernst Rutherford, while the Russian named it Khrushchevon after Igor Khrushchev. While these conflicted claims were being settled, the International Union of Pure and Applied Chemistry devises a hybrid Latin Greek numeral system of providing provisional name and symbol to all newly discovered elements. In some cases, the name were shortened by removing the repetitive letter. Be plus im can be written as bm or tri plus em can be written as trium. Let us name an element with atomic number 106 according to hybrid Latin Greek nomenclature. The name of this element is tri by combining together the root and the digit of the order of the digits, following by adding em in the ending. 106 is equal to un plus nil plus hags plus em called unneal haxium. The symbol for the element unyl with atomic number 106 is an H. Similarly, the name and the symbol for the element with atomic number 102 can be worked out. 102 is equal to un plus nil plus bm plus b plus em is equal to un nil bm. The IPSC name for the element with atomic number more than 100 are given below. The newly recommended name for the element with atomic number 104 to 109 are also mentioned. Comparison of actinides and lanthanide. Both lanthanide and actinide constitute element of F block as these involve the gradual filling of F orbital. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemble in some of their property but also differ in many properties. Let us review some of the important points of similarity and differences among the lanthanide and the actinides. Let us review some of the important points of similarity and differences among the lanthanides and the actinides. Point of similarities. Both the lanthanides and actinides involve the filling of f orbital. Both the lanthanide and actinide display predominating the plus 3 oxidation state in most of their product. Due to poor shielding of 4f and 5f electron, both lanthanide and actinide show gradual contraction in the size of their atom with an increase in atomic number known as lanthanide and actinide contraction respectively. Element of lanthanide and actinides with the sum number of unpaired electrons display similar absorption spectra due to FF transition. Fifth, lanthanide and actinide are highly electropositive and are very reactive. Sixth, nitrate, sulfate, and perchlorate of trivalent lanthanide and actinide are soluble in water. 7. Hydroxide, fluoride are carbonates of trivalent lanthanide and actinides are insoluble in water. 8. Both lanthanide and actinide can be separately by ion exchange method. Point of differences. The important point of differences between the lanthanide and the actinides are: first, metal orbitals. It involves the filling of 4f orbital, it involving the filling of 5f orbital. Second, energy gap between f and d orbital. The energy gap between 4f and 5d orbital in lanthanide is very large. As a result, their chemistry is fairly similar. Actinides, the energy gap between 5f 6d in actinide is small. As a result, their chemistry is very different. Third, binding energy. Binding energy of 4f orbital are higher in lanthanide. Binding energy of 5f orbital are lower in actinides. Oxidation state. The most common oxidation state is plus 3, in addition to some lanthanides showing plus 2 and plus 4. The common oxidation state is plus 3, in addition to some actinides showing plus 2, plus 4, plus 5, and plus 6. Fifth, shielding effect. 4f electron exert greater shielding effect, 5f electron exert poor shielding effect. Sixth, ability to form oxocations. Lanthanide do not form oxocation. Actinide form oxocation in higher oxidation state. Example, UO2 positive, UO2 positive. 7. Color of the ion. Most of the lanthanide ions are colorless. Most of the actinide ions are colored. 8th, complexes ability. The tendency to form complex is small. The tendency to form complex is large. They do not complex with bonding ligand. 9th, radioactivity. All lanthanide except promethium are not radioactive. All the actinides are radioactive. 10. Coordination number. Lanthanide display coordination number 6, 7, 8, 9. Actinide display higher oxidation number 8, 9, 12. Basic nature. Compound of lanthanide are less basic in nature. Compound of actinide are more basic in nature. Thank you.